Welcome to Module 5. What is noise? So from a perceptual perspective, noise is anything that interferes with achieving a specific object. So for example, background chatter in a library can disturb focus. Even the soft classic guitar sound can be considered as noise if someone is sleeping in the same room. From the physical point of view, noise refers to a random wave whose intensity values over time are correlated. So sinusoids and so signals are functions where through a mathematical equation given a certain value, it is possible to predict the previous and the following one. This cannot happen for noise signals due to the uncorrelations between intensity values over time. So the more a signal is noisy, the more intensity values are uncorrelated over time. On the opposite side, the more a signal, sound, is harmonic, the more intensity values are correlated over time. Noise is also characterized by a flat spectrum, so which means that all frequencies components have the same amplitude. So now you can see an example in this plot. In the video, you can easily hear the sound produced by a noise signal. There are different types of noise, each with unique characteristics. The white noise is a signal with a flat spectrum, meaning that all frequencies have the equal intensity. These create a constant and varying sound, often used for masking other noises. And then the pink noise. As seen in previous module, our perception of frequency intensity is not constant across the spectrum. Our perception, in fact, has a lowered sensitivity to low frequencies. In order to feel the same sound sensation at lower frequency, a higher energy is needed with respect to higher frequency. You can remember the phone. In order to be compliant with the phone measure, in fact, pink noise is similar to white noise, but with more energy in the lower frequencies. So you can see the difference between white and pink noise in the picture. Its intensity decreases by 3 dB per octave as frequency increases, giving it a balanced, less harsh sound. So it has been considered an intensity decreases by 3 dB per octave, since, as seen in previous modules, an octave step doubled the frequency difference. This reflects our logarithmic sensitivity on frequency discrimination from lower to higher frequency. So in the video, you can hear the sound produced first by a white noise, then by a pink noise. You can also notice the difference between the two spectrums, and you can easily see the decrease for the pink noise. White and pink noise are invaluable tools in acoustic measurement. For instance, the frequency response in a room refers to how the acoustic characteristics of room influence the sound waves across the audible frequency spectrum, typically from 20 Hz to 20 kHz. It describes how certain frequencies are amplified, attenuated, or altered due to the interaction of sound waves with the room's surface, dimensions, and contents. We can see here an example. If a room is composed by highly absorbing surfaces that act on 250 Hz, this will cause poor propagation, of course, of sinusoids at 250 Hz within the room. In order to measure the frequency response in that room, we diffuse white or pink noise into the space, since they are the frequency signals where all frequencies have the same intensity. A microphone then captures the room's response, identifying frequencies that are amplified or dampened by the room. This process helps in designing sound systems and optimizing room acoustics. Hence, when capturing the sound of a room, white or pink noise serves as a test signal due to its broad spectrum. Any frequencies the room accentuates will show up as a peak in the response, while those it suppresses will appear as dips. This analysis reveals the acoustic characteristics of the space, guiding adjustment for better sound performance. Let's move to the conclusion. We discussed the nature of noise and its practical applications, whether managing unwanted interference or using noise for precise measurement. Understanding its properties empowers us to create better acoustic environment. Thank you for your attention.